Hey guys, I'm really excited to be here, and by excited I mean extremely stressed. Um, my name's Philip. I work for Cybereason. We do endpoint protection and fashionable owl t-shirts. And my Twitter handle is pretty much my full name. So we're going to talk about lateral movement in WMI. We're pretty much going to have a quick intro to the scope of lateral movement, at least in this talk, and what WMI is, with a tiny peek under the hood. We're going to show some new and new-ish improved methods of lateral movement using WMI, and we'll have a word about how to detect all of these attacks and some others. So in recent years, there were lots of attempts to take network penetration and put it into some kind of geometrical shape. May it be the cyber kill chain, the threat lifecycle, the attack matrix, or my own hexagon of discomfort. All of them have a phase which is called lateral movement. Now, the scope of this phase changes between all of those frameworks, but in its core, it's pretty much this. You, as an attacker, have gained some kind of initial foothold, whether by exploiting some kind of vulnerability in an application or exploiting some kind of vulnerable user via phishing. And using this initial foothold, you've gained some kind of credentials. Now, you want to use these credentials to move to a machine which is a bit more interesting to you, which contains maybe other higher privilege credentials, or it contains the actual information you want to steal or show you can steal if you're just a red teamer and not an evil attacker. Now, of course, the scope of lateral movement has been expanded by stuff like Eternal Blue, but we won't be talking about exploits here. We're going to talk about using stolen credentials to achieve remote execution. Now, most of these lateral movement techniques are not bugs, they're features. This means you're not making an application act in a way it was not designed to. You're using some kind of feature, some kind of Windows feature, because this is a Windows talk, that is actually designed to allow remote execution, to execute remotely. This means nobody's going to close these as bugs, because system admins and other people are using these features, because sometimes you actually need to execute remote code. So the most common methods of lateral movement are remote service creation using stuff like PSExec or its in-packet implementations, remote task scheduling using AT or SCH tasks, and what's called today WMI lateral movement, a classic method of WMI lateral movement, which actually uses a class called Win32 process and a method called create. Now, why do we need additional vectors of execution? We have those three. They work if you have the credentials. They're mostly enabled on, I think, most networks. So it's not a challenge to get your code to run on another system. The actual challenge here is not to get caught. Unlike local execution vectors, exploits, persistent methods, etc., attackers still use pretty much those three methods to do almost all lateral movement tasks. And this means that if you can somehow monitor these things and look just for them, you're gonna catch lots of even pretty advanced attackers. So if you can somehow expand your arsenal of lateral movement techniques, you could shape how you look to the defenders, how you look to the network, so you can get caught in the noise, or you could exhibit some kind of behavior nobody is looking for and not get caught. Now, let's talk a bit about WMI, because all of these techniques I'm going to show are based on the WMI feature in Windows. So WMI was designed to allow network admins and programmers to interact with lots of unrelated elements on a machine, like processes and the registry and monitors, like both software and hardware, through one single API. If you want to obtain some information about anything that's represented by WMI, you basically pass through one single API and you say, well, can I please have the enumeration of whatever is represented by a specific class. WMI is an object-oriented model. And you could do this remotely through two protocols. One is DCOM and the other is WinRM, where the first is implemented on top of DCRPC and the second is implemented on top of HTTP. So the way WMI looks, or regular WMI usage looks, is that, as I said, you have classes which represent actual things on a machine, like the Win32 process class. And you could use an SQL-like syntax called WQL, or any kind of abstraction to it, and just ask a local or remote machine, hey, can you give me all of the instances of Win32 process? Or you could ask WMI to execute a method that is available on one of these classes. And this is done the same way, no matter what kind of thing the WMI class represents. Now, as you can see, WMI does represent lots of unrelated stuff. It could represent processes, but it also could represent what's called protocol bindings, which are basically network adapters. It could represent the registry itself, scheduled jobs, etc. And you would need to use lots of different APIs and write lots of code to access all of this information at the same time, instead of just using very, very similar code to have all this information just given to you. Now, to understand some of my techniques, you would need to know a bit how WMI works under the hood and the architecture of WMI. It's comprised of three main components. The first is the Win management service, the provider. The second is the providers, and the third is the repository. The Win management service, or the WMI service, is actually the face of WMI. Each time you, as a client, try to do any kind of WMI action, whether it be enumerating something, using a query, or invoking a method, you speak only to the WMI service. And it knows how to interact with every other part of WMI to allow you to gain the information that you wish, or to allow you to execute the action which you requested. The other part is WMI providers. WMI providers contain the actual implementations of the classes. This means if I want to enumerate processes using Win32 process, there's an actual implementation of that somewhere. This is not magic. And the WMI providers are COM DLLs or COM exes, which actually know how to implement all of the functionality that is needed from a class, and also know how to speak WMI back to the WMI service, which later gives back the results to the client. The third part is the WMI repository. These are basically a couple of files which are saved on disk, and they contain the whole definition of the WMI model, the definitions of classes, methods, and the association between classes and providers. So if we now go back to the Win32 process class, we can somehow understand how this whole lateral movement technique works. The Win32 process class, as I've said, represents a single process on a machine. And this class has a method called create, which basically is an abstraction of create process. So when you invoke the command, the PowerShell command that's behind me, what happens behind the scenes is that I communicate as a client with a local or remote instance of the WMI service, and I send out a request to use the create method of Win32 process with the supplied arguments. The WMI service checks which provider is responsible for implementing this method of this class, routes the request to the provider. The provider then actually executes whatever is needed to execute, returns to the service, and the service returns our return value to the user. Now, this is pretty much all of the classic, this one method is pretty much classic lateral movement using WMI. But there are actually a couple of ways to avoid using the Win32 process class to move laterally. And if you're if your adversary or the defender is looking for Win32 process, you could use some other stuff. So the first technique isn't really a new lateral movement technique, but it's an evasion technique, first publicly implemented by Matt Graeber. And it abuses the fact that WMI is an object-oriented model. And just like every single object-oriented model, it has a class hierarchy. This means that we could use a subclass, we could create a subclass of Win32 process and use this instead. So if we create Win32 not evil at all, using an API that WMI actually provides remotely, this new Win32 not evil at all subclass of Win32 process actually inherits all of the methods of the parent. And this means we could also get the create method. So we just call the create method on our new class, and we've avoided directly using Win32 process. Now there will be a short demo. I'm going to try to look at what happens in WMI using the WMI activity ETW provider, while I derive a class from Win32 process and just launch Notepad. So we're enabling the ETW provider. And this is a short script that just creates a new class remotely that inherits from Win32 process and calls create. So now we've launched an instance of Notepad, and we can see the events. And if you can't read it, this says exec method not evil at all create. And of course, we have Notepad. Now, what we're looking at is event 11 of this WMI activity ETW provider. This event represents all of the requests that are forwarded to the WMI service. And as we see, there's Win32 not evil at all. So if you're looking at Win32 process, you can't find it here. But you could find it in another event. How does this happen? We've created another class. We're not using Win32 process. Now, this kind of event, event 12, is actually the requests that are forwarded to WMI providers. And while we have created a new class, we haven't introduced any new code to the machine. This means something needs to implement that same WMI method. And it's still the create method of Win32 process. So if you know where to look, and you don't just look at the request to the WMI service, you could still detect this kind of attack. Actually, if you try to use some attacks which aren't really lateral movement, but involve deriving classes that do not have methods, like some popular persistence methods, like some popular persistent techniques, you don't see any provider method calls, so you don't really see any trace of the original class, which makes it a tiny bit stealthier. Another way to detect this kind of attack is by using WMI introspection. WMI allows you to look inside the WMI model itself and provides you an eventing system that tells you whenever a method is called or a new instance of a class is created. And when you use this query syntax to try to find new instances where target instance is some class, you actually look at all subclasses. This means that if I replace some class with Win32 process, this is going to catch my new WMI not evil at all class. I did try to do something a bit more stealthy, and I tried to use another method that the WMI system itself exposes, which is cloning a class. Now, when you clone a class, you don't have a child class. You have a class that implements everything, or at least has all of the methods, but it shares a parent with the original class, which means the hierarchy is a little harder to follow. But it turns out that the WMI service doesn't really know how to find that method on the cloned class. So this simply doesn't work. You could clone the class, but the moment you call the method, it just fails. Now, another category of new WMI lateral movement techniques is pretty much sprinkling WMI on top of the classic techniques. Now, this isn't supposed to help you unless you can somehow evade detection by sprinkling WMI over those techniques. And the way it helps you evade detection is by looking completely different on the wire. You won't see the packets that are used by other lateral movement techniques when you WMI-fy them. The first of those techniques is Win32 service, which represents a single service on a machine. And it provides you the whole capability of st.exe. This means you could start services, stop them, create new ones, and change existing ones. And this basically means that you could re-implement PSExec using WMI only. And if it's not enough, there are 4 classes which represent services on a machine. So you don't even need to derive new classes to use that old technique, to use the previous technique. You could just use one of those 4 that have the exact same methods to launch a new service on a target machine. So you basically need to beware of all 4 classes. Now, if you look at a Wireshark capture of PSExec or st.exe, you see that the protocol in use is DC-RPC, which is pretty complex, but the 2 things you need to know about it is that there's an interface ID field which identifies the service behind the protocol. So I could identify, hey, this is somebody's connecting to the service manager, and there's the operation number field, which determines the actual function called. There are some levels of encryption of DC-RPC, but even at the highest level of encryption, you could still find out that somebody is calling the create service function on the service manager. Now, if you implement the same thing using Win32 service, you see something else entirely. WMI, as I've said, could work over DCOM, which also works over DC-RPC. But all WMI method calls are actually transmitted over one interface and using only one function. And this means that if you're using this, you can't tell the difference between somebody calling a benign WMI method and somebody using a service or anything like that. You just know somebody called some WMI method, which is a bit more opaque. Another similar technique is old-style schedule tasks, which is basically an abstraction of the functionality of at.exe. Now, it provides you with a bit of a thin API, just like at.exe itself. If you want to enumerate jobs, you just enumerate instances of the class. And if you want to create a new job to run in at some time, you just use the create method. There's no way to run a scheduled job forcefully, but you could just always create a job that will run in a minute and take a quick bathroom break and return to code execution. But this will not run on newer operating systems. at.exe has been deprecated, and not only has the executable being deprecated, but the actual functionality behind the old-style schedule task has been deprecated in Windows 8 and up. And you won't be able to use the WMI version unless somebody has explicitly enabled this functionality on newer systems. But fortunately, we do have the new style schedule tasks, which are also represented by WMI. And this is represented actually by the PS schedule tasks class. And it provides the full API of schedule task.exe. But it's only available on Windows 8 and up. SCHtasks.exe is available on Windows 7, but the WMI version of it is gone, and you can't do anything to make it work. But it does give you a pretty rich API. This means you could register new tasks, you could run them forcefully, you could change existing ones, you could change the actions of existing ones and delete them. And another interesting thing is that there are a couple of commandlets in PowerShell 3 and up that are related to scheduled tasks, like the new scheduled task commandlet. And all of these are actually using WMI behind the scenes. So if you've ever used this in some kind of red teaming engagement, you might have been actually subverting some kind of IDS without even knowing it, because you were using a whole different kind of communication. Now let's see a quick demo. I'm going to install Meterpreter on a remote machine while I'm looking at the network traffic with Wireshark and looking at service control packets. So we have a Meterpreter listener. And we're looking at service control packets because we're going to start a new service, much like with PSExec. And we're just going to run Meterpreter as a new service using WMI. So we have a new session. Of course, we're system. And let's see how many packets we've generated. 0 service control packets, which is pretty nice. If this was an IDS looking for PSExec, this is exactly what it would see. So another lateral movement method is the Win32 product class, which isn't a modification of an existing method or some kind of evasive technique. It's a whole new lateral movement method. And the Win32 product class represents applications that are installed by MSIExec. And it has a very handy method called install, which allows you to install basically any MSI file. You also have the admin, which is administrative install method, which could also be used to install MSI files. And you could also use the upgrade and configure to do some other stuff. And fortunately, even Metasploit allows you to package your payload as an MSI, but it basically only allows you to package exe and DLL payloads. The MSI format itself allows you to use VBScript and JScript inside of an MSI. So you could basically just use something like .NET to JScript, embed it into an MSI, and run it with this and without using any commonly known execution vector. And there are historically pretty advanced groups which have used MSI payloads, but I haven't seen anybody use an MSI payload using this. They were basically dropping an MSI payload on disk and then using PSExec or something else, not really using this whole MSI format and what MSIExec allows you to do. And again, a short demo. As always, Meterpreter. I'm just going to use the install method to install it. This actually throws an error because I don't really want to install anything. I just want to run my payload and not touch the registry. Now, this has a TMP file executing as a child of MSIExec because this is the Metasploit version, and because, well, I'm lazy and I didn't write some kind of JScript version of a payload. But you could just as well substitute it for any MSI payload you want. Now, I did try to do other stuff with the Win32 product class. First, I tried to replicate the MSIExec/y option, which basically turns MSIExec into a version of run DLL32, and it allows you to load an arbitrary DLL. Now, there's simply no way to do this via WMI, which is pretty sad. Another cool thing I thought about is by looking at uninstallers. Each installed application has an uninstaller command line path written in the registry under that application. And it's used when you're using the add or remove programs dialog. It could just use MSIExec, or it could run that specific command line. So I tried to use the uninstall method of Win32 product to basically run a command line which I inserted into an existing installed application, which sounds great, but it just doesn't do anything. So, shame. Another technique is abusing WMI providers. As I've said, WMI providers are where all of the class instances and methods of WMI are implemented. This means that if you could somehow run your own WMI provider in the system and you could load it remotely, you're basically running code on the machine, which is exactly what we want. Now, a guy called Alex Leary has shown a method to register a new provider purely using WMI functions during last DerbyCon. And he's actually written a really cool WMI provider POC malware, which acts as an actual WMI provider. But I had two problems with this method. The first is that you actually need to write some kind of DLL that's WMI compliant and drop it on the disk. And if I can avoid disk, I prefer to do that. And the second part is that you really need to write a WMI provider which works and write lots of WMI code, which, at least in C++, looks absolutely horrible, and I'm a lazy person. So I really don't want to write an actual working WMI provider. What I do want to do is just make this whole provider loading functionality load an arbitrary command line, because arbitrary command lines are the best. To do so, we need to have 3 steps. First, we need to create a COM object, because WMI providers are COM objects, and that's how they're implemented. Second, we somehow need to register this object as a WMI provider. And third, registration isn't enough. We want to actually load our code. So let's start by creating a COM object. To create a COM object, you basically only need to modify the registry. You need to add a subkey of the relevant class ID you've chosen for your object, which is the GUID shown here, and add an implementation. Now, if your implementation is an exe, you add it under local server 32. If it's a DLL, you add it under inproc server 32. And whenever this object is called, is an instance of this COM object is created, this is what gets loaded. The second step is to register a WMI provider. Now, the WMI providers are actually represented themselves by a WMI class, which is _Win32 provider. And this is a pretty big class. It has lots of properties, but there are basically only 2 properties that interest us as bad guys, because we don't really want it to work as a good WMI provider. We just want it to load. The first is a name, because we need to somehow reference our WMI provider. And the second is the class ID, which is the ID of the COM object, which we want to load. And there's a third one, which is the hosting model. The hosting model tells us how do we want to load our WMI provider when it loads. You could load it as an independent exe with system privileges, or you could load it as a DLL into one of several host processes. So if you've ever seen those pesky WMI PRVSC processes running on your machine, these are actually WMI provider hosts. And the reason there's multiple hosts, it's because they're running as different users. Some of them need to be running as a system, while others are better off running just as local service host or network service host, because they don't really need those privileges. So it seems that if you just create an instance of this _Win32 provider class, that's it. You've registered your own WMI provider. And you can choose your own class ID. We're going to choose the hosting model to be self-host, which is a special model that loads your WMI provider as an outside exe with system privileges. And if we really wanted, we could just switch up the the hosting model and provide some kind of DLL or something like that. But as of now, we're going to stick with self-host. But we still need to somehow load this provider. Now, how WMI providers are loaded normally is on demand. That means that if something is asking for a class which is implemented by a provider that's not up, WMI loads up that provider, and that's it. Now, if you don't remember, our WMI provider is PowerShell running calc, which really does not implement any WMI class. So we need to find another way to load this, because nobody's going to demand our WMI calc provider. It turns out there is a way, which is the MSFT providers class. This class represents all WMI providers currently loaded on a machine. And it has a handy method called load, which basically receives the name of a WMI provider and loads it up without any demand beforehand. And as with every other WMI method, this is available remotely. So what happens behind the scenes, and I know this because this didn't work initially. The reason this didn't work initially is because I mistyped calc, but I did open it up in IDA because that was the first thought I had before checking if I mistyped calc. So this load method internally calls the server object raw factory create instance method, which pretty much unconditionally runs this block, which creates an instance of the object denoted by our class ID. This means that the first time anything checks our WMI provider is an actual WMI provider and not just a bunch of crap is after our code is running. And if our code's running, we don't care. So what happens is this function checks the local server 32 key under the relevant class ID. If we're using the self-host model, it runs our command line, and then it tries to somehow interact with it using inter-process communication and query different interfaces relating to WMI. It of course fails because this is not a real WMI provider, but we're already running and we could do pretty much anything we want. We have never wanted to actually implement a WMI provider. We just wanted to bootstrap our own code using this functionality. Now, there is a problem with the self-host hosting model, which is basically what we're using to run arbitrary command lines, and that every time you create a new WMI provider with self-host, there's an event log event that just says something like, this could be a real security issue, which is really not good if our goal is stealth, because a huge event saying somebody did this and that, and which could be a security issue, isn't really stealthy. Fortunately, the angel of backwards compatibility smiles on us, and because of old WMI providers, there's a special hosting model called network service host or self-host, which tries to load the provider as a DLL into a lower privileged host process, and if it fails, it just loads it as an outside process with system privileges. And this, of course, does not write anything to the event log. So if we can make it fail to load our DLL by, let's say, simply not having a DLL and having only an exe file, it will always default to running our code as system, as an outside process, without writing anything to the event log. Well, almost anything, because just like with COM hijacking artifacts, we haven't really implemented a real COM object, which will give you this very nice event that says that something didn't register with DCOM. This class ID is actually the class ID of our malicious WMI provider, but we could implement some kind of rudimentary COM functionality just to bypass this if we really want to. And another demo. This time, we're going to use WMI to write remotely to the registry of a victim machine. We're going to create a new COM object. And then we're going to register a new WMI provider which uses this COM object and load it, which will result in system-level execution. All right. So these were all of my new lateral movement techniques. But as I was researching WMI, I wanted to see what's the stupidest thing I could do with WMI. And that's messing with boot configuration. If you're not familiar with the BCD store or the boot configuration data store, this is basically how Windows knows how to boot. It contains entries about the boot manager and the Windows loader, which are the elements which load the kernel, among other stuff. And it turns out there are WMI providers which allow you to interact with BCD and manipulate it. And just like with every other WMI feature, it's available remotely. So we could basically change the files which are used by Windows to load Windows. So there are no profound boot security insights here, just this stupid thing. I'm going to try to open the BCD store and find winload.exe, which is basically the component that loads the kernel. And because I don't know how to write bootkits, I'm going to take winload and use WMI to switch it out with calc.exe. And I'm going to make the machine restart again using WMI. And later, we're going to see how Windows tries to boot from a calculator, which we could see in this demo. So here we have just a regular BCD configuration with winload.exe and the boot manager. We're going to override this configuration with calculator. And now if you look at the bottom, we have calculator as the Windows bootloader. And we're going to restart the remote machine. So if you've ever wanted to see Windows boot from a calculator, you could see this video. Did you really expect anything else? Don't boot from calc. And now, a word about detection. As I've shown in pretty much the first lateral movement method, the WMI activity ETW provider basically gives you all the information you need to detect all of these techniques and many others. It could show you every time a method is called, even if it's a derived method of a class that you created. It could show you each time a new instance of a class is created, each time there are changes to the WMI model, such as new classes or new providers installed, and each time a new provider is loaded. So this basically covers all of my techniques, and I think you could use it intelligently to cover each and every WMI attack seen in the wild and probably most future ones. Unless you actually exploit WMI somehow without using its built-in functionality. Another great method, which I've also shown, is WMI introspection. The WMI eventing system allows you pretty much everything the ETW provider allows. It's just a bit less, it's a bit slower. So if you can use the ETW provider, just use that. But you could also see pretty much every method call, instance creation, and in some cases, even the arguments sent to the methods, which is pretty nice. Now, the things I've shown are only relating to WMI providers and classes developed by Microsoft. But you could write your own WMI providers, as we've seen with our malicious provider-ish thing. And vendors actually use this functionality. So depending on your software and your hardware, you could have a much larger attack surface because of people not thinking thoroughly at what their WMI providers expose. Because if you can use WMI remotely, you can use all WMI classes remotely, such as this laptop has a WMI provider for its BIOS, and I can remotely change my BIOS password and then enable it and restart my machine, making it pretty much a brick. Again, not really useful, but really annoying. And you could probably use this, and you could probably use lots of other software vendors, providers to do lots of evil. And this is why you really need to know what WMI providers and classes exist on your specific machine, and also look at WMI as a whole, and not just at specific techniques used by one attacker or another. So I've actually written a POC tool which implements everything but the stupid BCD thing, and you could get it at the Cyberies in GitHub. And also, if you want an article version of the slides, which provide a tiny bit more information, you could check out this link. And of course, I keep posting tiny offensive techniques on my Twitter, so if you're interested, you could just follow me. Thank you. So, questions? Right then.